about today. Error bounds are also referred to as the Lagrange error bounds or the alternating series error. So there are the two. Oh, that would help with it. So we've got the Lagrange error bound or your alternating series error. Those are the two different errors, and they are very specific in terms of the AP exam, which error they're going to want you to use. Even if it's an alternating series, you can still use the Lagrange error bound, but very rarely will they ever ask you to use a Lagrange error on an alternating series, but you could. Obviously, the alternating series error bound you can only use on an alternating series. So there are two ways to calculate the error, like I said, in your Taylor polynomials. One is if you have your alternating series. It could be referred to as your alternating series error bound or your alternating series remainder. Again, if your polynomial has alternating signs and it converges to some limit, the error is found by taking the absolute value of the first neglected term in the series as the terms get smaller and smaller. So we'll talk about what they mean by that first neglected term here momentarily. The Lagrange error bound. If the polynomial does not alternate signs, then we use what's called the remainder estimation theorem. The remainder estimation theorem is your Lagrange error bound. Again, the words are used interchangeably, and we'll take a look at exactly what the difference is in a few minutes. So what we're going to concentrate on first is we're going to take a look at your alternating series remainder. So like I said, if you have an alternating series that converges and it decreases, then the absolute value of the remainder approximating the sum by S sub n is less than or equal to the first neglected term or the next term in the series. So in words, this is what we're talking about. So S represents your infinite sum, or what the actual sum is. Your S sub n is what the partial sum is. This A sub n plus 1 is your first neglected term. So, in words, the absolute value of your error is going to be equal to the absolute value of the actual sum minus the partial sum. And this is going to be less than or equal to your first neglected term. That's the big thing you need to remember about your alternating series error. It's about the first neglected term. The error can be no more than whatever that first neglected term is going to be. So the alternating series remainder, the alternating series error is a much easier, and when I show you Lagrange in a little bit, it is a much easier error to calculate than Lagrange. Like I said, you can use the Lagrange error bound on alternating series, but sometimes they won't give you all the pieces of the information you need in order to use Lagrange. All right, so let's take a look at an example. Approximate the sum of the following series by its first 6 terms. What is the error bound using the alternating series remainder? So again, first of all, what I need to do, they want me to approximate the sum of the series by the first 6 terms. So again, what I want to do is I want to write out the sum of my first 6 terms of this particular series. So I have my negative 1 to the n plus 1 times 1 over n factorial. Now notice my lower index is not starting at 0, it is starting at 1. So what is the first term for this particular series going to be? The first term is going to be what? When I plug in a 1 for n, that's going to be 1. Plus, plug in a 2. So that's going to give me negative 1 over 2 factorial. Plug in a 3. So that's going to give me 1 over 3 factorial. Plug in a 4, that's going to give me negative 1 over 4 factorial. Plug in a 5, that's going to give me plus 1 over 5 factorial. And then finally, minus 1 over 6 factorial. So the questions asked me to approximate the sum of the following series by using the first 6 terms. So I've generated my first, second, third, fourth, fifth, sixth terms. So this is where I wanted to bring in the calculator. So let's come up with what this sum is going to be equal to. So again, using my calculator, I've got, again, 1 minus 0.5 plus 1. Everybody remember where the factorial sign is on the calculator? So 1 divided by, again, if you need the factorial sign, you go under math, go all the way to the right to PRB. It's option number 4. Or, 3 factorial 6. You could do it that way, too. Minus 1 divided by your 4 factorial. Plus 1 divided by your 5 factorial. Minus 1 divided by your 6 factorial. You always want to take these decimals out because some of these you're going to see that the remainders are very, very small. So you definitely want to take these decimals out to about 5 or 6 decimal places. So this approximate sum is going to be about 0.063194. And this is your partial sum of the first 6 terms. Yes,
Just a quick thing. If people want to find the factorial symbol faster, then you can just do an alpha window.
Oh, really? See, you guys know all alpha window.
And then it should be 9.
I don't have 9.
Oh, never mind. It's only for like the colored ones.
I could probably update you may actually be able to update your operating systems on that. I'm going to try and update my operating system. But yeah, so some of you may have it under Alpha 9. Thank you. Alpha window. You may, like I said, Sam, if you don't mind in a little bit, I'll try and update my operating system and see if we can spread the good news around. Thank you. So alpha window 9 is where you can also find. All right, so any questions, guys, on how I calculated the first 6 terms? So now, because they want me to use the error bound using the alternating series remainder, the absolute value of the error is going to be less than or equal to the first neglected term, which is a sub n plus 1. This sum is based upon the first 6 terms. So the first 6 terms of this particular series is completely accurate. So that's why this error can be no more or less than the 7th term, because that is my first neglected term in this particular sum, which I know in this particular series is going to be 1 over 7 factorial. So 1 divided by 7 factorial, so 7 factorial is going to be equal to 1 over 5,040. So this is how close this partial sum using your first 6 terms is to the actual sum of the particular series. That's what this error is telling you. So what this error is telling you, remember the definition of the error, it's the actual sum minus the difference between the partial sum of the 6 series. This difference has to be less than or equal to 1 over 5,040. So when they ask you for the error bound, what you're doing is you're making a compound inequality. So I know that the actual sum of this series, whatever it is, which I'm going to call S, is going to be greater than or equal to the sum of my first 6 terms minus this error bound, or it's going to be less than or equal to that infinite sum plus the error bound. So my actual sum is going to be within 1 over 5,040 less than the actual sum, or it's going to actually be 1 over 5,040 greater than the actual sum. So if I actually come up with a value here, again, I know what S sub 6 is, which is that 0.63194. And I subtract from that 1 divided by 5,040, or 1 over 7 factorial. That gives me a value of about 0.63174. Less than or equal to the actual sum, which is less than or equal to, if I take my 0.63194 and add the 1 divided by 5,040, that gives me 0.63213. 6321214 if I round. So that's how close your partial sum is to the actual sum of that particular series. All right, so any questions on calculating the error bound? So the question asked me for two things. It asked me for what is the approximate sum of the series by the first 6 terms, which was right here. Then the bound is this particular inequality right here. Okay. So any questions on that particular example there? The big thing about the alternating series error is whatever you generate your Taylor-Maclaurin polynomial out to, it's going to be the next term that's not included in that particular estimation. So let's take a look at example 2. Estimate cosine of 0.2. Again, this is telling me to use a 4th degree Taylor polynomial about a is equal to 0 and find the error bound. So I know that this is a Maclaurin series. So first of all, what I want to do is I want to generate my Maclaurin series for cosine of x. Now, we haven't used any of our Taylor-Maclaurin series to do any estimations. So we're adding that piece into this particular section. So I know that my Maclaurin series for cosine of x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. So there is my 4th degree Taylor polynomial. So now I'm going to use this to estimate what cosine of 0.2 is equal to. So cosine of 0.2 I can find by approximate. Again, this is going to be an approximation. What I'm going to do is I'm going to plug in 0.2 into this particular Taylor polynomial for x. So 1 minus 0.2 squared over 2 factorial plus 0.2 to the 4th over 4 factorial. So again, cosine of 0.2 then is going to be approximately equal to, and again when I type this in my calculator, gives me about 0.98007. So what you found, again, my actual sum is what f of 0.2 is. So that's actually what cosine of 0.2 is equal to. My partial sum is what the approximation is based upon my Taylor polynomial of that 4th degree, so p sub 4 of 0.2. So my partial sum is based upon what the approximation is using that 4th degree Taylor polynomial is. So any questions on how I've estimated cosine of 0.2? So now remember, the error. Again, finding my error bound, it's an alternating series, has to be less than or equal to the first neglected term. So since this is omitting all of the odd powers, the next neglected term in this particular series is going to be the absolute value of my 6th term. Again, this is my first neglected term. So in my 6th term, I know that in this particular polynomial, it's x to the 6th over 6 factorial. so that I can plug in 0.2, so 0.2 raised to the 6th power all over 6 factorial. Now again, I know this would actually be negative, but remember I'm taking the absolute value of the term. So when I type this in, 0.2 to the 6 divided by 6 factorial. Now notice I'm getting a really, really, really small number in scientific notation. So again, this is going to be equal to 8.88889 times 10 to the negative 8th. So just leave it in scientific notation. Yeah.
Would you still say an plus 1 for the neglected terms for this?
Yeah, because it's the next neglected term. I mean, technically it's an n plus 2, but again, it's the next neglected term. If I was to expand out the series, it would be the next term.
All right, so if you put that down, they wouldn't mark it.
No. Because I can't use the 5th term because that's 0. So, all right, so now it's asking me for the error bound. So the error bound, remember, is that particular inequality. So again, I have to take my partial sum that I used to the 4th degree. I have to subtract the error, which is at 8.8889 times 10 to the negative 8th. That's going to be less than or equal to S, which is less than or equal to S sub 4 plus 8.889 times 10 to the negative 8th. So I'm going to subtract from that. Let's see. So first I'll add, since I already have it up. So that's going to be 0.98. So that's going to be 0.98007. Less than or equal to S. Less than or equal to 0.98007. Minus the 8.88889 times 10 to the negative 8th. So 0.980066. So you can see how close these Taylor and Maclaurin approximations are to the actual value of the functions. So some of these remainders are really small. Like I said, you'll have to take these decimals out a lot further if they're really, really close. All right, so any questions on the alternating series error bound? Another way they may ask about this question, again, they're giving me my series. Show that 1 minus 1 over 3 factorial approximates f of 1 with an error less than 1 over 100. So when you take a look at the series they're giving you, 1 minus 1 over 3 factorial represents the first 2 terms in this particular series. So this is my S sub n. So we want to approximate f of 1. That's the x value. So the first neglected term in this partial sum is this particular term right here. So this is the error. If I'm estimating f of 1 only using my first 2 terms, my next neglected term is this x to the 4th over 5 factorial. So remember, the absolute value of the error when you're dealing with an alternating series has to be less than or equal to the absolute value of the first neglected term. And in this particular case, it's going to be my 3rd term, which is, in this particular series, x to the 4th over 5 factorial. Again, I'm using this to estimate 1, so I'm going to plug 1 in for x. So I'll end up with 1 over 5 factorial, which is actually 1 over 120. So I'm showing that this S approximates f of 1 with an error less than 1 over 100. Well, I know that 1 over 120 is less than 1 over 100. Another way they sometimes write this particular error, we know that it's actually representing the absolute value of S minus that particular partial sum. And in this particular case, the actual sum is your f of 1 minus S of n is representing the first two terms in this particular series by plugging in that 1. So 1 minus 1 over 3 factorial. And this has to be less than or equal to 1 over 120. But a lot of times on the AP exam, they'll write this particular notation right here. Remember, this just simply means the actual sum minus the partial sum, or the actual value minus your estimated value. That is what the error is. It's the difference between your actual and your approximation. So any questions on your alternating series error and how you calculate it? All right, let's take a look now at another one. Every FRQ that I've seen on the AP exam, one part of the question is always about the error bound, whether it's Lagrange or whether it's alternating. They always have a question on the FRQ about the error bound. So here is a Maclaurin series evaluated at x equals 1/2 is an alternating series whose decrease in absolute value to 0. The approximation for g of 1/2 using the first two non-zero terms of the series is 17 over 120. Show that the approximation differs from g of 1/2 by less than 1 over 200. So now remember, my true sum, which is my S, is actually the g of 1/2. My partial sum is the sum of the first two non-zero terms, which is that x over 3 minus x to the third over 5, which they've calculated for me to be 17 over 120. So remember, the error, the absolute value of the error, is going to be equal to the absolute value of S minus S sub n, which is going to be less than or equal to A sub n plus 1. So my actual value, g of 1/2, minus my partial sum, which is the 1 over 3 minus 1 over 5. Again, looking at these first two terms, this is what my partial sum is being evaluated as. This has to be less than or equal to my next neglected term. So this x to the 5th over 7 is my next neglected term. So again, I'm simply going to plug in a 0.5 in here for x, because again, I'm doing that estimation for 1/2. So it should be 0.5 to the third over 7. These should be 0.5, not 1. Because it's not an x value of 1, it's 0.5. These should be 0.5 right here. I'm sorry? Yeah, 5th, thank you. Yep. 5th, yes, this is the 5th. I can't. Thank you. I'm having trouble seeing. So this is 0.5 over 3. This is 0.5 to the third. There you go. So then the absolute value of g of 1/2 minus 0.5 over 3 minus 0.5 raised to the third over 5 has to be less than or equal to. And when I take 0.5, and raise it to the 5th,